Welcome to this first chapter in real-time rendering fundamentals. We're going to look at what happens underneath the surface. That means we're going to take a look at a mix of different solutions. We're going to look at what scalability is and why it's important, the fact that we have deferred or forward rendering and what they mean, the word gbuffer and what it stands for and how it impacts rendering, and a brief word about vertex and pixel shader basics. So real-time rendering is essentially a very big mix of different solutions. Real-time rendering is really complex and demanding, and because of that we need to use different kind of solutions mixed together, and we try to offload what we can to pre-calculated steps. So first of all, you should look at real-time rendering as being divided in two groups. Part of it is going to be pre-calculated. Part of it is going to be actually real-time rendered. And often, many things that we do are a patchwork of different solutions duct taped together essentially, because we have such a specific challenges to overcome that that's usually the only way forward. For example, the occlusion system is a very good example of that. Occlusion means to determine what can or cannot be seen. In other words, what should be rendered in this frame and what should not be rendered in this frame. Something that's behind the wall should not be rendered, so that should be occluded. But the act of determining what is actually seen and what is not seen, the occlusion process is a 3 to 4 stage process, depending on how you set it up. And one of the steps in the occlusion process is going to be pre-calculated, whereas the other ones are actually real time. And there are 4 different solutions as well, because it's rather difficult to figure out what is visible or what is not visible, so you end up with many different solutions. And that is something you're going to see come back at various places in the Unreal Engine and the editor. You're going to see different features, different solutions, and it might be a little bit confusing in the beginning, but this is the reason why it's like that. Then you have scalability. Now, the rather unique thing about real-time rendering is that it allows you, and also requires even, for changing the graphical quality, essentially the rendering quality, at any time. So while it's running, it should be able to scale itself and make it run faster, make it run slower, higher quality, but run slower, and so on. It should be able to scale. That is scalability. It allows the content to scale itself to run on many different kind of devices. A game or an application should be able to run on maybe a mobile device, but it should also be able to run on a high-end PC, and the content should be able to deal with scaling back and forth. This ability for scalability is deeply interwoven in the engine and the tools. So you're going to see this come back again and again and again at many different places. For example, you have the R commands, and I'll show you that in a second. Let me just read the last line. Performance is an important part of real-time rendering for most applications of it, and maintaining good performance is a combination of mastering those scalability settings and correctly altering the content. So it's really both of them. It's about controlling the R commands and the other settings that are part of the scalability system, but it's also about, of course, correctly setting up the content, having the content be well optimized, and so on. But if you look at those R commands for a second, I can go to the editor. We have a level here. It doesn't really matter which level it is. This is the level performance _ example level. If you're interested in getting this particular level, which is in the folder lighting _ rendering fundamentals, finished assets, and here's the level. This is the level I'm going to use at different sections of this course. Either way, one of these I believe has shadows set up. Let's see which one. You don't necessarily have to follow what I'm doing here. I just want to demonstrate for a second what it does. You can see there's dynamic shadows here. An R command, you can get that by opening the console, which is the tilde key being that, or that, which should be on the top left of your keyboard underneath escape, but on some foreign keyboards this might be harder. So if that doesn't work, the fallback would be to use the output log over here, and if you don't have that in turn, you can open it up by window, developer tools, output log. Either way, either there or in the console, and I have the console here at the very bottom now, you can type r dot and then many of the commands you can pick from. And these are the scalability commands. So to give you an example of a good one, r.shadow quality, which scale the quality of the dynamic shadows while it's running, while the application is running, in this case the editor. If I do r shadow quality 0 and we enter that, we essentially turn off the shadows entirely. So you can try that, just type that in one of these places. You can see the shadows have disappeared. If you do this again, when you do shadow quality 1, you get shadows, but they're really bad quality. They're pretty jaggy and simple, etc. 2, 3, 4, and I think 4 is the maximum. It might be 5 as well. But that's essentially scalability, the act of changing the graphics and the rendering quality while the application is running. And that's a very good thing to take into account as you're working with the tools and the engine. Now, there is 2 ways of rendering. There is deferred rendering and there is forward rendering. And that's not just an Unreal Engine, by the way, this is in general. No matter what software you use, no matter what engine you use, you will have either deferred rendering or you will have forward rendering. So two ways we can approach rendering things in real time. The Unreal Engine is deferred by default, but can also do forward if you would configure it to do so. Deferred, however, works best for the majority of content. Now, I'm going to greatly simplify this, because this is roughly how it compares, but again, it's greatly simplified. You could say that deferred gives stable and better performance for more demanding applications, whereas forward gives faster performance for simpler uses or when the hardware is limited. That's roughly the idea, but again, it's not that black and white, but essentially all the large blockbuster games you see, for example, they usually are deferred. That's also why Unreal tends to be deferred by default. Deferred gives better performance and more stable performance for higher end applications, and most mobile games you see, a lot of VR games you see, or VR applications or VR mobile applications, they are usually forward. So essentially it goes like this. You will use deferred unless you're making something that is going to run on something with limited hardware power such as mobile or VR, then you probably should consider forward, otherwise stick to deferred. Deferred also supports more rendering features, so that's another reason why deferred is usually preferred. But the weakness in deferred is the anti-aliasing, which is better in forward due to technical reasons on how the whole thing is set up. So forward tends to give you better anti-aliasing. In deferred, you only have TAA, temporal anti-aliasing. And temporal anti-aliasing is what causes the slight amount of ghosting you see in the frames. And again, this is not unique to the Unreal Engine, this is in general to most real-time renderers. Anytime you play a game or real-time application, you see a slight amount of ghosting. That is because of an inherent weakness within deferred rendering, which forces it to only use temporal AA, and temporal AA in turn causes some ghosting. And again, just to be clear here, if you're new to it, this is probably a lot of terms and might be a little bit confusing, but just to point out, most documentations, most tutorials, most other content you will find online on the Unreal Engine will be based on deferred rendering. So if you're uncertain about this, just stick to deferred and just treat everything you see as being about deferred, because it probably is. Then you have a word called the G-buffer. A deferred renderer will use a G-buffer. A forward does not actually, or it could, but it gets, or some hybrids are possible, but too much detail there, so let's just say it can't, whereas a deferred one can. A G-buffer is essentially a set of images for each frame. These images contain all the information required for the later stages of the render process. Essentially what we're doing is we're doing real-time compositing. We're rendering out a screen in different versions of the screen, and then using those different versions, which are grouped together in the G-buffer, we can use those different images to figure out other stuff further into the rendering process. For example, how do we apply fog to the scene? In order to apply fog to the scene, we need to figure out what the depth is of the environment. So we're going to capture the depth in a G-buffer pass earlier on. This happens entirely in the background, so it doesn't really impact your day-to-day work, but it's still important to understand that it's there and what it does to give you a little bit of perspective on why real-time rendering is good or not so good at some things. And let me just very quickly show you this, because it's easy to visualize this. This is a program called RenderDoc, which analyzes a frame you can capture. So you can capture a frame in the editor or in-game, and it will analyze that. This is not an Unreal Engine tool, it's again a general rendering tool you can download, but there is an Unreal Engine integration for it. This captured a particular screenshot or particular frame from this level from the editor, and you can see here this on the right side is the G-buffer. It's different images. The combination of these images together, all of these images together, that is the G-buffer. You can see the name also says G-buffer D, G-buffer C, G-buffer B, G-buffer A. And you can see this is the screen more or less as you see it, not entirely. You can see there's materials missing and such. This is capturing the direction of the pixels. This is storing, if you were to look at it separately, the metallic materials, the specular values of the materials, and the roughness values of the materials. This is base color only, and then there's a couple of special ones. That is the G-buffer. And then lastly, you have pixel and vertex shaders. Now, during rendering, often very simple calculations have to be repeated over and over and over again, a huge number of times. And this is really slow to process on regular processors. So a general all-purpose CPU of a computer or other device is not really made to run millions and millions of tiny little calculations over and over again. It's fairly slow in doing so. So what we've done is we created hardware and software dedicated to only doing that kind of work. Those are the shaders. The various types of shaders are essentially small calculations run again and again on a dedicated part of the GPU hardware. They are at the very heart of how we render in real time, and they therefore have a significant impact on how we render and where performance is lost. Switch to the editor here. A very clear example of that is if you move all the way out, you can see there is fog on this level. In fact, now I turn the fog off, now I turn the fog on. A pixel shader would take an input value For example, it takes the input value of the pixel there in the middle of the screen, it takes the input value, and then it figures out it is this far away from the camera, the far color is this, there is this much far color and it's this kind of color in this particular location, therefore I'm going to take the color as it was, color of the pixel without fog, apply this much blue color on top, and then I'm going to write that pixel again, but with this color applied to it. That is a pixel shader in action. So every single step almost of the rendering process is done using pixel shaders, where it modifies the value, recolors it essentially, and then outputs it again. So an input value is taken, for example the current color of a pixel, calculation is applied, and a new value is output. Pixel shaders work per pixel, vertex shaders work per vertex. So essentially all real-time lighting, all shading, the rendering of materials, fog, post-process effects, and a great many other things, they're all pixel shaders. So this is extremely central to the rendering pipeline. And you're going to see that word come back time and time again as you work with real-time rendering. Right, so we've gone through some of the things that happen underneath the surface, the fact that it's actually a mix of many different solutions, both pre-calculated solutions and just different real-time solutions. The concept of scalability and how it's an integral part of the tools and the engine. The fact that you can render real-time in two different ways and roughly when you would use deferred and when you would use forward. The idea of a G buffer and the concept of vertex and pixel shaders and what they are.